Hello and welcome to Charged and Ready. This is a Youth Climate Summit session with me, Becky, and I volunteer for an organisation called People Power, which is trying to build community action around sustainability. Today I'm going to talk to you a bit about energy and power, how do we energise the UK, batteries and their relevance to renewables, and it's going to be a bit interactive, so you might want to take a moment to have a pen and paper handy. Okay, well first before we get started, I wanted to ask you a question. How energised do you feel today? On a scale of 1 to 5, where 1 is basically you could fall asleep at any minute, and 5 is I'm here and I'm ready for anything. Okay, have you got a number in your head? Let's say it out loud in 3, 2, 1, 5. If I was met by resounding silence then, I'm going to assume that you're all feeling a bit sleepy, but hopefully after this session you might feel a little better. But let me ask you one more question. How powerful do you feel today? Does that feel a bit like a weird question to ask? Well, it is important because when we're talking about energy usage, we talk in units of energy and power. Some of this you might already know from physics lessons, but energy is how we quantify an ability to do work. For example, to move an object from A to point B, or to switch on a light. And some units of this are joules and also watt hours. And then power allows us to quantify an amount of energy transferred or supplied per unit time. So rather than asking the question, how much energy do I need to turn a light on? We ask, how much energy will that light use per hour? And this is measured in watts, which equals a joule per second. And watts and watt hours are the units you would typically hear in conversations about energy. Looking at the underside of my kettle, and I'm sorry it's a little bit dirty, we find a label which shows us a power rating in watts. So, as you can see from the red box, this kettle has a power rating of 2,500 to 3,000 watts. So this kettle uses a lot more energy per unit time than my 40-watt light bulb in my bedside lamp. A challenge for you all is to have a look at some of the labels on electrical appliances you have at home and see which have higher power ratings and use more energy per unit time. But right now, over to you. Where do we get our energy from in the UK? You have 30 seconds to scribble down as many energy sources as you can on a piece of paper, starting now. What's 20 seconds left? That's 10 seconds. Are there any fossil fuels that you'd forgotten about to add? Have you thought about renewables as well? And that's 5 seconds left. All right, so did you get any of these? If you don't recognise some of them, maybe ask your teachers what they are after the session. One you might not have heard before is imports. And a fun fact for this session is that actually the UK imports electricity from other countries such as Poland and France via interconnectors, which are huge long cables underneath the sea. So I found this great online resource called mygridgb.org, which you can find on the internet. And it's a website which has all these infographics which shows where the UK gets its energy from and how it's distributed over those different energy sources that we've just listed. And as you can see from this infographic here, this is showing the distribution of energy from the last 12 months in the UK. And you can see the units are in watt hours, like I mentioned before. And also you might notice that the UK has quite a large reliance on natural gas. So if we're thinking about renewable energy now, and we're thinking in particular about solar energy, could you sketch a graph to show how much energy we can harvest from the sun in 24 hours? So we have 30 seconds to do this in, starting now. So we can see from the y-axis, this is the amount of energy that you can harvest at any one point in time. And then the x-axis is the time of day. And I've added some times like midnight, midday, and midnight again. So try and think about when the sun is brightest. And does it always shine? Okay, that's about 30 seconds time. So did your sketch look a bit like this? So we can see a maximum and minimum in the amount of energy that we can harvest from the sun. And the maximum, as you might expect, would come around midday. And then as nighttime falls, the sun isn't shining anymore and we get minimum in the energy that we could harvest. Bonus points if yours was more complex with some more peaks and troughs, depending on whether it's cloudy or not. So let's add to this sketch now. So now you have 30 seconds to sketch on top of this graph the amount of energy we use from just lights over the course of the day. And it's not to scale, so don't worry about that. We're just looking at the maximum and the minimum. So you've got about 20 seconds left. So think about the times when you turn on the lights and you're home, and the times when you switch them off and don't really need them. So 10 seconds left. 5. Okay, did your sketch look something like this? So we tend to switch the lights on when it goes dark. So that's why we've got some maxima at either end of the day, and then a minima around the middle where it's all bright and sunny. We don't need the lights as much. So this shows how when we're considering using renewables, there could be a mismatch between the energy that's available at any one time and when we actually need to use it. So if we're thinking of wanting to transition away from using fossil fuels to using renewable energy like solar or wind, there are some things to think about. Like, when does the sun shine and when does it not? When does the wind blow and when does it not? And the same with hydroelectrics as well. Do these sources provide us with constant energy, or are they a bit more chaotic? And that's where the term intermittency comes in. You might have heard it bandied about in discussions about renewable energy. And it's this idea that often renewables are more chaotic systems with lots of peaks and troughs in the energy that's available to be harvested, and they don't provide a constant source. So a solution to intermittency is storage. And this is the idea that whilst the sun is shining, we find somewhere to store that energy, and then we can draw on those stores when we need it. And one of those storage solutions is batteries. So what's inside a battery? If we opened up a battery, and don't try this at home, we would find layers and layers of electrodes termed anode and cathode, and a plastic separator between them. And also we would find a liquid called electrolyte. And in a cylindrical cell like this one, or one that was in your remote controls, they would be all rolled up together like a Swiss roll. So how do they work? How do they store energy? They work by performing electrochemistry, which is an area of chemistry where you use electricity to make chemistry happen, or vice versa. And when we are thinking of electrochemistry, we need to be thinking of electrons and redox reactions. Redox reactions are where reduction and oxidation reactions are occurring. And again, you might have visited these in your chemistry lessons. So over to you again. Which of reduction and oxidation do you think describes a gain of electrons, and which do you think has a loss of electrons? Can you fill in these blanks? Okay, so well done if you said reduction is a reaction which gains electrons, and that oxidation is a reaction where there is a loss of electrons. So these reactions are occurring in the anode and cathode, which allows a battery to convert between electrical energy and chemical energy. So how can we observe electrochemistry in action? How can we start to visualize the energy contained within a battery? Well, there is a simple setup we can use to observe colour changes that indicate electrochemistry is happening. For this we need some graphite rods, universal indicator solution, a battery, some salt, some water, a petri dish and some beaker, and some wires. And I found this experiment on YouTube. So here is an image of the experiment all set up. And can you see the swirls of colour in solution? Universal indicator that we added just a few drops of indicates the pH of a solution through colour. You may have seen a pH scale like this before. And pH is a measure of H+ ions in solution and can help us see what the electrons are up to. So a red colour is a measure that there are higher concentration of H+ ions, or a depletion of electrons, and consequently a more acidic solution. And purple colour indicates a lower concentration of H+ ions, or a buildup of electrons, and a more alkaline solution. So here you can see the colours of red and purple are coming from different electrodes. And this is because the battery is providing energy to perform electrolysis of water, which means splitting the water molecules into hydrogen and oxygen gas. And unfortunately you can't see this from the image, but doing this experiment in person you would see bubbles of gas forming at the graphite rods. And by looking at the half equations, we can see how the electrons are involved and what the redox reactions are. So here are the half cell equations. So in the first equation, a loss of H+ ions and electrons is liberating oxygen gas. So do you think this is an oxidation reaction or a reduction reaction? Well done if you said oxidation. And in the bottom equation, electrons are combined with H+ ions to liberate hydrogen gas. So again, is this oxidation or is it reduction? Well done if you said reduction. And redox reactions are also happening inside the battery as well, at the anode and the cathode. The plastic separator allows for ions like lithium ions to transfer between the electrodes, but not electrons. So these get forced around an external circuit instead, which can then power a load such as a motor or a light bulb. So now we understand a bit better about what's inside batteries and how they work by electrochemistry and redox reactions. We've talked about energy and power and their units and relevance to household appliances. And we've thought about renewables and how storage can help solve the problem of intermittency. And batteries aren't the only solution out there for storage. Maybe ask parents and teachers about the other ways of storing energy. And you also might learn some others through other Youth Climate Summit sessions. So we're going to finish this session with some visions and missions. And my vision statement is we want a world in which everyone has access to safe, secure and sustainable energy. And an action for you all now. Think about the ways of reducing energy use. Because as we saw from that graph from mygridbeak.org, we still are very reliant on fossil fuels in the UK. So reducing energy use is a very direct action that we can implement now as individuals to lower our carbon emissions. So now we have 60 seconds and write down one behaviour you would change at home to save energy and one that you think would be implemented in a classroom. Starting now. There might be a lot of things that you already do. Is there anything more that you could add to that? Maybe you could think about some of the climate sessions that you've had during this the Youth Climate Summit, and is there any things that have been suggested there that you could add? So about halfway through. Maybe you could think about what we've talked today about and the power of different appliances at home and how much you use them. About 20 seconds left. If you've already finished, feel free to show a partner or a friend what you've written and explain why. Great. Fantastic, and well done everyone for being so interactive with this session. So now you've got those written down, can you be the lead of that change? And then finally, a call to the world leaders at COP. I want to see more investment in green energy solutions, and I want to see more work and cooperation towards making these accessible to all countries and all people. So you've been listening to Charged and Ready, a Youth Climate Summit session brought to you by me, Becky, from People Power. Thanks for listening.